Hey YouTube, what's up? Dr. T here, and welcome to the Altcoin Express and my hometown, St. Petersburg, Florida. So for reasons I can't remember now, I got interested in computer science in about June, about this time of the year in 2015. From Wikipedia, computer science is a humongous area. There are very, very many ways to go, and usually there are some core requirements, and then you split off at university into a subdirection of interest. Mine specifically is in the area of artificial intelligence, a subfield of computer science. So we'll pop over here. Artificial intelligence in and of itself is a humongous area, and as I said in previous posts, I'm kind of generally getting around to nibbling the Bible. So machine learning, computer vision, image processing, robotics, data mining, and we are interested in a subfield of machine learning. So we will go there. And machine learning in and of itself is quite a big area. I'm really not interested in machine learning. It mainly has to do with complex fields associated with classification, but I am interested in a field that has been evolving recently because of the fact that technology like TensorFlow and GPUs are enabling mass data sets of data to be able to processed and used. So I'm interested in the area of reinforcement learning. Now that is the area of code that will drive your car for you. It'll play AlphaGo. It'll develop those things, and the basics of this come from reinforcement learning. So we'll just briefly read this. Reinforcement learning is concerned with how an agent ought to take actions in an environment so as to maximize some notion of long-term reward. Reinforcement learning algorithms attempt to find a policy that maps state of the world to the action the agent ought to take in these states. Reinforcement learning differs from supervised learning problems in that the input-output pair are never presented nor suboptimal actions explicitly corrected. I'm going to take a break here. To the best of my knowledge, there is no detailed study courses in reinforcement learning. There is one lecture in the computer vision thing which I'll put up shortly. So I went to David Silver's lecture series and bravely plodded into this and the corresponding book online PDF file by Sutton from University of Alberta. I got completely swamped out of my bird for a long time, and that's just the theory. Coming around how to learn to code anything and how to go about doing it. Well, I belaboured at the beginning of the year for quite a long time, actually before the beginning of the year. Sort of got through his course, sort of got into with all things in computer science or reinforcement learning, it comes down to coding. Can you code something? Because if you can't, all the math under the sun doesn't get you anywhere. So that started the Grid World project off. Stop now for a minute. So I'm working on Grid World as part of the project to learn the basics of this, and it's introduced in this course by Peter Abel from Berkeley, which I shall be continuing forward with shortly. So this comes from lecture 10 of that series. It shows the grid and the agent moving around, and when it gets to these various points it picks up a reward. I won't go into how that's kind of used, but it's fed back through the grid and you kind of have to get over here. Now I've got most of the code done for this, got some problems to work out in terms of how to get the data onto here, and then the colors changed. But as far as the grid's concerned, we can go and take a quick look at that. The code I've upported to, oops, I just dumped it. What an asshole, golly. It's easy to see the code on my GitHub, so I've just uploaded this code. I'm not here to impress you, it's just the fact that I have gotten these skills down. This is the graphic parts of it. That's how you get the agent to move around. When it gets to its goal, it needs to be reset. And we have to get the agent to move around in all directions and then reset it. So that's how much that code is. There's a whole ton more to go on here in terms of getting the data in, but that's somewhere else. So if we come over to the code on my coding environment and run it, and I've just got it to stop when it reaches the goal. So a couple of examples of it moving around there. Learning how to code a neural network, even a single hidden layer, is quite a to-do. I spent many hours last year doing this and got some of the basics down. And it relates to this course here, taught and designed by Andrew Karpathy, who taught it prior to graduating and then moving on to OpenAI and then on to Tesla as Director of Artificial Intelligence. This is the place to go to learn all the ins and outs of neural networks, although they're focusing on vision. And I have got some of those basics down now. So if we come over to my neural network folder, there's a lot of stuff in here. I've played around this for hours and hours and hours. I never went beyond a single layer because it's difficult to do. And we can take a look at one of these. So it's easy to look at this in my GitHub. You're not expected to understand, follow, understand, or get any of this. But basically, this is one example. It brings in some data here, which I got out of putting in real numbers to just put in some just static data. This static data has to be operated on by activation functions. The classic was sigmoid functions. We moved on to better operating functions. There are two here. There's a tanh function and a relu function. Once again, you're not supposed to understand or follow anything of this. Generally speaking, you randomly select the weights, so-called weights, but I have developed some other algorithms that gives you a little bit better step into that pathway. So they're offset, and I'm just uploading a set of data that I've developed somewhere else. Training is a very problematic thing because I can't get into it. It's too complicated. But basically the guts of it is this is a forward pass through the neural network, and the math part of it that involves all the calculus stuff is in the back propagation part, and this just gets run over a whole bunch of cycles, and then it gets some data presented out and we see how good the data is. So in the coding environment, this is the self-same thing. We can run it and it will start crunching numbers down here. So the home prices represented by these artificial numbers are categorized by this little data set here, and basically it has to produce a estimate of what this would be after training, and that's what this data is here, having run the thing. So we can take a look at the data. This is just and the plot that comes from this. All right. So this is the plot of the. Once again, there's no point me trying to explain what this is. It's just the data that goes along with this as it improves its ability to see stuff. The issue here, I think, is that it's because a single neural network. It offers 95 plus or minus 100 plus or minus 5% efficiency from around the 65 point down to the 185 point, and I think that is because it's just a single hidden layer. But one has just got to get the basics of this stuff down, because this is all self-taught. It's monstrously difficult to get into, but once you get into it, then you're kind of on your way a little bit. So there are lots of tutorials on deep reinforcement learning. that teach you the nuts and bolts of it all. None of this lot teaches you anything to do with how to code anything, which is what makes this such a fun subject to trying to get your head into. So from another drawing of the topic, within some framework here, a lecture is given from this series.
The question we would like to explore is to which degree we can teach systems to act, to perceive and act in this world from data.
So that's what this is all about. It underscores robotics, it underscores autonomous driving vehicles, it deals with AlphaGo and all that stuff. So I'm kind of considering what might be the next useful project. This is above and beyond. This is graduate work. This is the kind of thing you would get into as in a master's degree, where you focus on this as a sub-subject. You'll be going on to do a PhD, so you'd focus on, you'd get a member of staff to take you on to do a master's degree, focus on deep reinforcement learning from a specialist, and you get taught how to do this stuff. I'm trying to teach myself on the outside of this without having a clue how to go about doing any of it, just got to gut it out and work it out. So that's where it is. And the next project, I think an interesting project, comes from electrical engineering, which has to do with robotics. Now, electrical engineering is all about building electronics, engineered electronics to manipulate, control and define robots to do various things. Preemptive of that, they use areas from within my framework of simulation. And one project that they've got outlined here is that of a robot coded to find its way around an environment. This comes from MIT's course on Introduction to Electrical Engineering. So I'm just going to play this a little bit because I think this is an interesting stepping forward stone to bring what I know of neural nets together, to bring what I know of reinforcement learning together, to find how to code a deep neural network to interact with the reinforcement learning and find how to use this kind of thing. So I'm just going to play this. It's kind of interesting. This could be the next topic. In fact, I'm quite interested in doing this.
On probability and planning, and the idea there is to learn about how you make systems that are robust to uncertainty and that can implement complicated plans that they too are robust to uncertainty. So there's a number of things that we will do, including creating maps of spaces that the robot doesn't understand, telling the robot how to localize itself, how if it woke up suddenly in an environment, it could figure out where it is, how to make a plan. And as an example, I'll show you the kind of system that we will construct. Here the idea is that we have a robot. The robot knows where it is. Imagine there's a GPS in it. There isn't, but imagine there is. So the robot knows where it is, and it knows where it wants to go. That's the star. But it has no idea what kind of obstacles are in the way. So, if you were a robotic driver in Boston, you know that you started out at home and you want to end up at MIT, but there's these annoying obstacles, they're called people, that you should, in principle at least, miss. Okay, so that's kind of the idea. So I know where I am. I'm the robot. I know where I am. I know where I want to be, and I'm going to summarize that information here. Where I am is purple. Where I want to be is gold. And I have a plan. That's blue. My plan's very simple. I don't know anything about anything other than I'm in Waltham and I want to go to Cambridge. So, blast east. So I imagine that the best way to do there is a straight line. Okay, so now what I'm going to do is turn on the robot. The robot has now made one step. And I told you before about these sonar sensors. From the sonar sensors, the robot has learned now that there seems to be something reflecting at each of these black dots. It got a reflection from the black dots from the sonar sensors. That means there's probably a wall there or a person or something that in principle I should avoid. So, and the red dots represent, okay, the obstacle is so close I really can't get there. So I'm excluded from the red spots because I'm too big. The black spots seem to be an obstacle. The red spots seem to be where I can't fit. I'd still want to go from where I am, purple, to where I want to be, gold. So what I do is I compute a new plan. Okay, then I start to take a step along that plan, and as I'm stepping along, okay, so now I think that I can't go from where I started over to here. I have to go around this wall that I didn't know about initially. So now I just start driving, and it looks fine, right? I'm getting there, right? So now I know I can go straight down here. Oh, wait a minute, there's another wall. Okay, what do I do now? So as the robot goes along, it didn't know when it started what kinds of obstacles it would encounter, but as it's driving, it learned, oh, that didn't work. Start over. So the idea is that this robot is executing a very complicated plan. The plan has, in fact, many subplans. And the subplans all involve uncertainty. It didn't know where the walls were when it started. And when it's all done, it's going to have figured out where the walls were and, provided there's a way, presumably find the way to negotiate the maze and get to the destination.
So I think something along these guidelines would be good for me for the next project. It's going to take a while. There's lots of things to learn. I mean, I've got to work it out all on my own, but there is a target project. So that said and done, I think we will work towards doing this as our next project in moving into the master level capability of coding in artificial intelligence with specialization in deep reinforcement learning and enabling a robot to find its way around a maze to a goal.